Although we write reactions as if they occur in a single step, for the most part they typically occur in more than one step. Each of these steps is called an elementary step, and what we want to talk about is the way these intermediate steps work in order to give the overall reaction that we're looking for. So to begin with, we'll look at what these individual steps look like. So here's an example of a fairly simple reaction between NO2 and CO to give NO and CO2. And what we see happening here is that the first thing is, so this is our NO2 molecule, and then this is another NO2. So two NO2 molecules react, and an oxygen is transferred from one to the other. So this one is actually an NO3, and then we're left over here with an NO. Then this NO3 reacts with a CO and gives us the overall, or the products that we see. So notice that this one that's formed here, this species, the NO3, doesn't actually appear in the equation, and we see it again here. So this is referred to as an intermediate, and these steps are referred to as elementary steps. So when you have a reaction that occurs between two different molecules or atoms, that's a bimolecular step or bimolecular reaction. So these are both bimolecular reactions. So the type of steps that we can have a unimolecular step, and in that case you would just have one molecule. So that would be something like one molecule just changing by itself. Most typically, you have a bimolecular reaction. That's the one, like the one that we just looked at. And then this one, the termolecular, is sort of unusual because that requires three molecules or atoms, ions, whatever it is that's reacting, to react all at one time. So you have to have three different things that come together with the right orientation, which we'll talk more about that factor a little bit later. In every multi-step reaction, there will be one step that is slower than the others, and this is what is referred to as the rate determining step. And it's this step that actually determines the form of the rate law. And if we were able to know what that step was, then we could know the rate law for any particular reaction. So we'll see kind of how that works out in a little bit. Okay, so first just a few details. The sum of all of the elementary steps must add up to give the overall equation, and these steps, which are referred to as the mechanism, must agree experimentally with the rate law that you determine by experiment. And again, we'll see what that means in a little bit. But anyway, this is what we mean by a mechanism. So a mechanism is the series of elementary steps that eventually give the overall reaction that we're looking at. So here we have a reaction that we've looked at before. This is the decomposition of N2O5 to yield 4NO2 plus O2. And we also have listed a proposed mechanism. In other words, this is a way that it's thought that this reaction might take place that is consistent with experimental data. So let's check the first prerequisite, which is that the steps of the reaction must add up to give the overall reaction. So one thing that we see right away is that in this first step we don't have 2 N2O5. So the first thing that we can do is we can just multiply through by 2. Okay, so now if we go through and we cancel out wherever we have the same thing on both sides of the equation. So on this side of the equation we have 2 NO3s, so there's 2, and then there are 2 on this side, and we have an NO on this side of the equation. We have 2 here, so this will be canceling out 1, and then there will be 2 more. We have an NO and an NO. So if we add this up, then we'll get the overall equation, unless I've made a mistake. No, I think that's all okay. So the other thing I'd like to point out here is that this mechanism consists of a fast initial step that's an equilibrium step, which means that the products can can change back to reactants at the same time. Again, this is fast. Then we have a slow step, and this would be the rate determining step, and then we have finally a fast step. So we'll see later exactly the significance of fast and slow steps. The other thing I should point out is that in this reaction we have intermediates forming. So there's an intermediate, and by that I mean something that appears in the mechanism that doesn't appear in the overall equation. So there's one intermediate, and another intermediate would be NO. So we have NO there and there. So here we have a hypothetical reaction, and we want to write the rate law that would result from this mechanism. In other words, here's the reaction up here, and we have a proposed mechanism, and we want to see what the rate law would be based on this mechanism. We can write the rate law for any individual step. So you should understand that that's not really a contradiction of what we've been saying. We can't take the overall reaction. We can't take this reaction and write the rate law based on this one. So we can't say that the rate is equal to the concentration of A times the concentration of B squared. We can write the rate law for this one. Okay, so let's do that. So when we write this one, it's just going to be that the rate is equal to the rate constant, concentration of D, times the concentration of B. But this presents a problem because in this equation we have D, and D doesn't appear in the overall reaction. So we can't have an intermediate that appears in the rate expression or the rate law because we can't measure the concentration of an intermediate. So we do have a way of dealing with that. So if you notice up here, we can write what the equilibrium expression would be for this first reaction. So the equilibrium expression is just the concentration of the product, so in this case that would be D, raised to whatever exponent is equal to the coefficient. So the coefficient is 1, so we just have that. And then over the reactants. So the reactants are A and B. Now, we see that we could rearrange this. So we could see that D, so the concentration of D, is equal to the concentration of K. So this is the equilibrium constant times the concentration of A times the concentration of B. So we can substitute this expression here into what we already have for D. So when we do that, we're going to end up with, I'm going to move this up just a little bit, so we'll end up with the rate is equal to, so we're going to have A, so it's K, concentration of A, times, and then we have B times B, so that's going to be B squared. So let me emphasize what we've done here, because none of this may be entirely obvious. So we have a proposed mechanism, and I'm going to talk more later about what this means to say a proposed mechanism, so I'll get back to explaining that idea in a little bit. So the proposed mechanism looks like this. We have A and B that react to form some intermediate. Then that intermediate reacts with B to form C. So that if we add everything up, then what we have is that the intermediate cancels, and we have our overall reaction. And remember, that's all this is. This is simply the sort of the net reaction that takes place. Now, in the mechanism, we have the slow step, and we can write the rate equation for the slow step here. But the problem is the slow step, which is the rate determining step, contains an intermediate. So we have to figure out a way to write that expression, that's this expression, but without d. So we write the expression for the equilibrium, and then we rearrange, and then we substitute. So we substitute this in for d. What we really are doing, you don't need to worry too much about this, but we're actually combining two constants. So technically speaking, you've got one constant there and another constant, and those two constants become another constant. So you could call this one K1, K2, and then you end up with K3. Okay, so this is the type of thing that you're going to be working on in the next little bit.